안녕하세요. Good morning. 네, 안녕하세요.
Recording in progress.
All right. I think we can get started. So how I hope that the the first project, project one last week was not too difficult. Judging by the number of participants today, I guess it was too easy. So everybody felt very confident, so they don't have to come to the class. I guess that's a good sign. Was there any comment or feedback that you wanted to share before we start the class about project one or how you used LLMTA to, get some help for your project? Any comments generally? What made was the project too hard or too easy? What the general impression or any technical difficulties, whatever. But if you have something to share, feel free to speak up. All right, so in case somebody's typing something, I hope that oh, there is a comment from Namho. I think the difficulty was good for a project to do within 24 hours. As I said, I would assume 90% of the attendees of this class would probably have done it within 30 minutes, I guess. If you just ask, Claude or GPT-4o, you can just get a working code and just, fine tune the hyperparameters and you're done, which would take less than 30 minutes. The right difficulty? Really? These days, people just can code without the knowledge of actual coding using LLM. I wouldn't imagine that it would take more than 1 hour. I mean, given that you have an undergraduate degree in computer science, then, you know. But maybe that's just me. Maybe some people just didn't use LLM to get help for your project one, which is admirable because the less you use the less you depend on the LLM to do your coding, the better or more you learn. Because if you just blindly rely on the LLM to do coding for you, you wouldn't learn much. So, but the question is, do we need to really learn coding at all? Because in the future, LLM will actually do most of the coding for you. So, do we actually need to learn coding? It, I guess the answer depends on the individual. Comment 기욱. However, I think the target accuracy was quite reasonable to achieve within 24 hours using limited resource, more than I initially expected. I guess, sure. I mean, because you're using Colab, so I guess that's also a bottleneck. Right. And as I said, as I announced in KLMS, there were some varying degrees of mistakes or not hitting the target accuracy, the target performance. And it was really hard to draw a line between what is acceptable, what is a condonable mistake and what is not. So we just decided to just let one failure slide unless you, except for project three. Project three, you have to pass because that's the pinnacle of what we learn in this course. But you can either fail in project one or two. You can't fail both times, but at least if you fail one time for project one or two, we'll let this slide. So if you've passed project one and if you're super confident that you will pass project three, then you don't have to do project two. I'm gonna have to mute everybody. as I said, if you're confident that you will pass project 3, then you don't have to do project 2, because as I said, one project, you can fail one project as long as it's either project 1 or project 2. Question from Namo: will project 2 be similar in difficulty? I think all projects are super easy because I told you to use LLM explicitly. So if it's just about passing the passing the course, it's all the same. If it's about learning the actual material, it's a different story, because project 3 will be vastly more difficult to truly understand what's going on. But as long as you're in for the passing grade, I think it's all the same. Also, the TA session going through the project guideline was really helpful. Okay, that's good then. But you can always ask the LLM TA about all the specific specs. So, you know. Question from Halakim: I wonder how others met the target accuracy without using pre-trained model. We didn't use pre-trained model. We just asked Claude 3.5 to code a specific CNN architecture for the fashion MNIST, and we just got that score. So I don't know why you would have to use pre-trained model. If you use pre-trained model, it will be super easy. If you just use if you just download a VIT something like large, which is trained on the JFT Google data set, it will be super easy to pass the passing grade. All right, so I guess there are no more comments. We have some material to I mean, today it's not very technical. It's more like a history class rather than a technical class, because word embedding used to be a big thing back in 2013, 2014, maybe up to 2018 and 19, but now we're in the age of LLM, so word embedding is kind of like a given knowledge. But it's really helpful to understand word embedding because everything started from word embedding, the modern deep learning NLP. There is a bunch of literature and also whole field of study of NLP pre-deep learning era, where we used to study the syntax and semantics, parse trees, part of speech tagging, named entity recognition, which is still relevant in some applications, but those were the things back in the day, like pre-2012, pre-2020, I mean pre-2013. But since the dawn of deep learning, word embedding was the very first field of study, I would say, like deep learning based NLP topic that everybody was interested in. So this kind of sparked the possibility that maybe it's possible to use deep learning for NLP, because deep learning first shined in the computer vision field, not NLP, because 2012 was when AlexNet came along. So deep learning certainly worked well for computer vision, but people didn't really think about how to use it in NLP. But then word embedding became a thing, and then it stayed to be a thing until 2018 when BERT came out. And then BERT survived more than 2 years until 2020, 2021. Then after that came LLM in 2022 winter, which is ChatGPT. So it's really helpful to get the context of how NLP evolved over time. So in that respect, this is more of a history lesson than a technical lesson. All right, let's move on then. So today we're going to talk about word embedding and document embedding, subword encoding, which is also a very important piece of topic, not discussed a lot these days, because again, these are all default knowledge and such a given piece of technique that we use. And then contextualized word embedding, we're not going to go into the detail. We're just going to talk about the concept, because we're going to learn BERT separately 2 weeks later. So what is a word embedding? So every word in NLP, in text processing, word is the unit of computing or unit of processing text. So, and we need some way to vectorize it, because we have to vectorize it. If you want to put anything into a computer, into a machine, it has to be a vector. It has to be a numerical value. It has to be vectorized, right? So for example, we would like a word cat and a kitty to be vectors where they have similar representation, because cat and kitty are similar in meaning, right? So if they're semantically similar, then we would like those vectors, corresponding vectors, to be also similar, meaning, for example, short distance, or having a like high cosine similarity or high inner product score, something like that, right? As opposed to hamburger and cat, which is not so relevant. So we would like these two be similar in the latent space, in the vector space, as opposed to cat and hamburger, which should be way more far apart, right? So we briefly talked about this concept of vectorization or latent embedding in autoencoder, right? Autoencoder, we talked about MNIST images, and we said that like image of one should be more similar in the latent space as opposed to image of 5 and 1, which should be way different, way far away, right? So it's the same thing. Image digit 1 versus digit 5 is like cat versus hamburger, you know? So the typical, like the most naive form of encoding or vectorizing a word is to use one-hot vector, right? For example, if we're talking about blood types, A, B, and O, there are 4 blood types, then we can just simply use a 4-dimensional vector, and each position represents something. Each, like, first position is A, second position B, third position AB, the fourth position being O. So it has to be one-hot, like one-hot meaning only one of 4 dimensions can be one at any given time. So this is the most naive way of looking things, you know, like vectorizing things, and it's also interpretable because when we look at this, we immediately understand this is A, this is O, this is like AB, like it's human interpretable. But the problem is, if you vectorize anything, just, you know, like for example, words using one-hot encoding, it's too naive to actually, you know, capture the semantic. For example, if we assume that the horse has a vector form like this, and zebra has a vector form like this, where I guess the 5th dimension is horse and 4th dimension from the back is zebra, then these two will have a inner product of 0, obviously, right? Because they're orthogonal. So, you know, if you just inner product the two, it's going to be 0. But it's not just between horse and zebra, it's between any 2 words, because each dimension represents exactly 1 word. Like this is dog, cat, boy, car, horse, something else, like truck, airplane, whatever, right? So any 2 words will always have a inner product score of 0 and Euclidean distance of square root of 2, because that's how one-hot vectors are. So which is a bad idea, because we would like to have horse and zebra to be more closer in the latent space as opposed to horse and desk, because they are semantically, you know, dissimilar. So one-hot embedding doesn't really capture that kind of semantic similarity, or actually it doesn't capture anything, because one-hot embedding always gives you inner product of score 0 or Euclidean distance of square root of 2. So it doesn't capture anything. It's just human interpretable, but that's it. So there's a bit of a better representation of documents. Well, when we were talking about word embedding so far, but document embedding has been studied for a very long time, even way before like deep learning, because this has been studied in like information retrieval and that kind of stuff. So document can be based on counting words inside a document. For example, if this is document 1, this is document 2. Document 1, John likes movies, Mary likes 2. Document 2, John also likes football. If you just count the number of words occurring inside a single document, then this will be document 1's vector. This is a vector, right? 1, 2, 1, 0, 0, 1, 1. So each dimension represents something. For like first dimension is John, second dimension is likes, third dimension is the movies, right? So this is 1, 2, 1, 0, 0, 1, 1. Document 2, based on this word counting, is 1, 1, 0, 1, 1, 0, 0. Then their inner product or cosine similarity will not always be like these, because now we have similarity captured by counting things. So if 2 documents have a very severe overlap between the 2, like counting wise, then their inner product or cosine similarity will be high. If the 2 documents are talking about vastly different things, you know, no overlap between words, then their inner product or the cosine similarity will be low. So document vectors based on counting actually works pretty well. But then these days, this is also not a very popular technique. There are other vector representation of words or documents for that matter. We could use I mean, these are specifically document representation rather than word representation, like document embedding, like counting based embedding, or You can go a little bit further using linear algebra techniques such as like singular value decomposition or non-negative matrix factorization. Or you can use like probabilistic topping modeling or probabilistic document modeling. So latent Dirichlet or latent Dirichlet allocation, LDA, was a big thing, I guess, in like mid 2000s until like late 2000s before, Word2Vec came along. So these are all related to document vectorization or document embedding, all before deep learning. So word embedding, starting with the 2013 since 2013, word embedding has been a thing. But even before that, do we have it? Let me see. Yeah, even before 2013, there were like very notable works that tried to vectorize words using neural network based approaches. Way back in 2003. Obviously, Yoshua Bengio. And also, very well-known work is Colbert and Weston from, I guess they were back in, they were in Meta, Facebook for some time, but I'm not sure if this was from Facebook. Anyway, there were some notable works, but I guess this is the one that sparked the word embedding field of study, since 2013. So the idea is distributed. Do we have, yeah, distributed vector representation? So distributed means as opposed to one hot. One hot has just one plane. Only one dimension is one, and all the other dimensions are zero, right? As opposed to that, distributed meaning we're going to use real valued vectors as opposed to one hot vectors to represent words. So like this. So we have a certain semantic that we want to represent, which is a cat. And when we're using one hot vector, then this would be its representation. But when we use a distributed vector representation, people don't call this anymore. This is terminology used way back in like 2013, 2014. But anyway, the meaning being we're going to use real values. So the good thing about using real valued vectors to represent meaning or to represent stuff or words is that for example, if you take this to be 1 and this to be 0, then this whole thing will mean a vastly different thing. It could be a dog or a boy or girl or a truck. It could be a completely different thing. But if you perturb this a little bit, like if this was like 35.2 or 94.3, this would still be like cat. Like there is no longer a definitive numerical value that represents cat because it's just a distributed value. It's a real value. So small amount of change doesn't really, make a lot of a difference. And that is why the illustration has a clever like blurriness in the word cat here, because this is definitely a cat, because this is clearly, this is dog, this is car, this is truck, this is cat, this is girl. Like everything's clearly defined. But in distributed representation, nothing is like clearly defined. It's all in the vicinity of certain semantic. So that's why. So this is the distributed representation. This is one-hot representation. And so the question boils down to how do we learn this value? Because this is not learning. We have already rule-based dictation for everything, like for first dimension being boy, girl, truck, car, airplane, whatever, right? But then for this kind of representation, how do we actually learn appropriate values to represent a cat or a dog or car, boy, whatever? So that would be the question. And the Word2Vec is such a easy algorithm that enables to learn a very robust and also semantic capturing representation. So we'll get to that. So before we actually talk about the algorithm, the strength or the merit or the impressive thing about Word2Vec is that it captures, even though the training algorithm is super simple and it's all based on like linear operations between vectors and stuff, but at the end, the outcome of this algorithm, the outcome being the word vectors, they seem to capture semantic relationship between words so well. So this being a very typical example. So let's assume that there is a two-dimensional coordinate. This is 0. This is x and y. So this is a two-dimensional vector. Then every word is a vector. Like there's a man vector here, right? There's king vector. There's like uncle vector, and so on and so forth. Like there's like woman vector. I'm not going to draw all the arrows. Anyway, so you can assume that each word is a vector in a two-dimensional plane, right? So you can do like operations between the two. For example, if you can subtract man vector from woman vector, and you can subtract uncle vector from aunt vector, right? If you do that, then the difference vector between these two these pairs being do I have another color? Yeah, let me just erase all these red things. If you do that, if you do the difference between these two, between these pair of vectors, then you will always get the same, not exactly the same, but more or less the same vectors. So which means that this vector element here, like this here, this represents the relationship between a man and a woman form words, like woman, man, aunt, uncle, queen, king, actor, actress, like Superman, Superwoman, something like that. So that is the impressive like achievement of word2vec, because a simple vectorization of words can actually capture the semantic relationship between words by doing like vector operations. So you can do interesting stuff. For example, you can do like this kind of operation. So uh queen minus king. Actually, there's a better. Let me draw you a better one. So um let me see. What we can do is king minus man plus woman would give you a queen vector, which is just exactly, I just use the term. If you put king over here, then it's the same thing, right? So basically, you have a king vector, right? There's like man vector, woman vector, concol vector. So there's a king vector, and then there's a man vector, and then there's a woman vector. If you do this operation, then the end product, the outcome that you get will be most similar. So I shouldn't actually use this, but it should be this. Would be most similar to the queen vector because of this relationship capturing vector between these pair of words. So that was this was like very a big thing back in 2013, 2014. People were actually really surprised by this kind of operation being actually possible at all. Because if you try to capture this kind of semantic relationship with numerical representation, like vector representation, and somehow try to train it, that would be like people would think that would be basically impossible or really tricky to do. But word2vec, as we will see, is such a simple algorithm, and it works like magic. So this was a very, very big finding or discovery back in 2013, and this actually sparked all the NLP, deep learning based NLP works afterwards. So it's a seminal work, even though nobody uses it these days. And yes, there are some other examples, like this is man-woman relationship. So sister, brother, niece, nephew, and uncle, woman, man, like yada yada yada. So um, note that these vectors are actually like 100 dimensions or 200 dimensional vectors, but the author just downsized it using PCA, or I think they use PCA to plot it in a 2D plane, just like how we used the scatter plot in autoencoder, right? This is a company CEO relationship. So like Chrysler's CEO is some guy, United Airlines CEO is some guy, IBM CEO some person. I don't even know if this is a guy or a woman. Like Verizon some person. So but you can see that the relationship, the difference factors between the two are more or less the same. Like they are magnitude wise and also their direction wise very similar. And the last one being the city and zip code. So Brooklyn zip code this, Buffalo zip code that, and yada yada yada. This also, this one's also interesting. Comparative and superlative. So slow, slower, slowest, short, shorter, shortest, strong, stronger, strongest. You can see that they are all following similar patterns. So like this kind of pattern, right? Like this. And this not just works in this doesn't works in this just doesn't work in English, but it also works for Korean. So Wonjae Kim is currently, if I'm not wrong, is currently like a machine learning engineer researcher in Naver, And back when he was, I have personally know him. Actually, we worked together. So back when he was an undergrad student, like way back, I don't know, like some 8 years ago or whatever, he actually learned Word2Vec and then tried to apply it in his Korean and then show it and share this result on his blog or something. So you can see it actually works pretty well. Like Barack Obama vector, negative minus 미국, America plus Russia will give you a Vladimir Putin vector. And so on and so forth. If you're familiar with like Korean culture, this would come very familiar to you. And also something very interesting, such as the one of the favorite is this one. So 소녀시대 minus 소녀 plus 아줌마 is 아이유. So that's how Korean citizens felt back in 2015, 2014, 2015. Yeah. Um, I oh yeah, this one's also very interesting. Akaraka is like a college festival from Yonsei University. So Akaraka minus Yonsei University plus Korea University 고려대학교 gives you 입실렌티, which is Korea University's college festival. So this works really well. This kind of Word2Vec algorithm is not language specific. It's language agnostic. So as long as it's human language, it works all the time. That's how powerful it is. Right, so before we get into the algorithm, any question? Question from Kang Jae-un. What about homonyms? Actually, that's a good question. First, I need to know what a homonym is. I used to study all of that, but I forgot. Homonyms. Homonym is a 동음이의어. Oh, okay, so it's a homophone. So it's a word that has the same surface form but has different meanings, such as what? I think, yeah, that is a very fitting question. That's a very good question because by the end of this class today, we're going to talk about exactly that. And for example, a word stick can mean two things. So stick can mean two things. Either it's actually like a wooden stick, like something that you hit with, or it's you stick to something like you attaching something to like a surface or something. Like that would be also stick, right? So stick has two meanings, and if you use Word2Vec, it's probably going to be very difficult to have like contain two seemingly independent meanings into a single vector form. So we're going to talk about that later, but that's a very good question. Word2Vec, yeah, there's a serious limitation when it comes to handling homonyms. But we're going to continue with the Word2Vec algorithm, unless someone else has a question. If not, let's continue. So the idea of Word2Vec is can be described succinctly by borrowing a quote from some person. I don't know who this is, but this quote always comes up. You shall know a word by the company it keeps. So which means that a word, like a vector form of a word can be somehow learned by looking at its context or its neighboring words. So if neighboring words mean like co-occurrence between two words. So given a word cat, what is the co-occurrence probability or the likelihood of seeing one word with the cat? That would be the question. This is a probability, right? Then the word meow has a very high likelihood of co-occurring with the word cat, as opposed to potato, which has nothing to do with cat, right? And pet also has pretty high likelihood of occurring with a cat. Occurring meaning like within the same sentence or within the same document, same paragraph, basically within the same context, right? So meow, flea, pet, they're likely to co-occur with cat in the context, as opposed to these three, which are not really, doesn't have anything to do with cat. So that would be the distributional hypothesis. So there are two forms of algorithm Word2Vec. Actually, the Word2Vec paper introduced two algorithms. So one is called SIBO, the other is called skipgram, and mostly people just stick to skipgram. So SIBO is just on a high level description. What you do is there are vector like, vectors that correspond to, actually, just let's start with an example. So I am a good student. So this is a sentence given to you. This is how many words given. I'm a good student. Let's add a period here. So 1, 2, 3, 4, 5, 6, 6-word sentence. And this is, let's say that there's t minus 1, t minus 2, t minus 1, t plus 1, t plus 2. So there should be a something in the middle, which we're going to use a. So this one. So this is the target. Then all the other are context or neighbors. So when A is a target, what happens in context word in SIBO is there is, oh, I forgot to draw. There are corresponding vectors for each word here, right? Which you need to learn because they are real valued vectors. So they're not one-hot vector, they're real value vectors, and they are randomly initialized as all parameters do. They are randomly initialized. So you can think of them as lookup vectors in modern NLP, like LLM NLP. So this is, so here, these 4 will be these, right? Because this is the target. This is t minus 2, t minus 1, t plus 1, t plus 2, t plus 2. So you take these 4 vectors and sum them all up, and then you want those summed vector to be very, very similar to this A vector, or at least be predictive of this A vector. So that's the spirit of SIBO. Skipgram is kind of the other way around. So you take the word A as a target, then using this A vector here, you want to be able to predict I vectors, M vectors, good vector, and student vector more than any other vectors. So you want, for example, given an A vector here, you would like to be able to predict I vector more so than other vectors that are not here, such as like dog vector, cat vector, whatever. So we're going to talk about that. So people use skipgram a bit more often, or way more often than SIBO, because skipgram gives you this kind of behavior, very, very, like it shows a very strong the semantic behavior here, like this. All right. So we're gonna move on to, this is basically the same thing. So this is how word-to-vec algorithm works, more and more like how skipgram works. You can see that there's a T here. T is just all the words in your sentence. So I'm gonna borrow that. Let me see if I can. And oops, I want to be able to copy this. Okay. Cool. And I'll just put it here. All right. So T here, oops, no, not this one. T here would be, using this example, would be 6, because there are 1, 2, 3, 4, 5, 6 words. So T is all the words in your document, in your paragraph, wherever. And this M is the size of your window, size of your context. So, oh, I forgot to talk about this. So there's like a window size you have to define before running this algorithm, because it's based on, for example, here, the window size is 2, because it's looking at 2 neighbors on the left and 2 neighbors on the right, given the target in the center. So that this is a hyperparameter that you have to choose. So it could be 2, it could be 3, it could be 4 or 5. It's up to you. So that will be the window size M. So we're gonna probably use like 2 here. Then you're looking at 2 neighbors on the left and 2 neighbors on the right. If you use 3 here, then actually there's nothing here, but you can go up to 3 here, right? So that would be it. And this is a log likelihood, actually more like a softmax likelihood more than log likelihood. So softmax likelihood, and since this is the target, these are the context or the neighbors. So these are given the context, given the target. I'm not sure what you see, but given the target, which is the A vector here, we want to be able to predict these, which are these 4. As I said, we want to be able to predict the neighboring words, or the words that are in the context. So this is your A vector, and this is either I or M or good or student vector, depending on where the J is in this M range, right? So this is your A vector, this is your neighbor vector. So you want this to be larger than all these. So this is kind of like a normalizer. So you can see that this W is just all the words in your vocabulary or your dictionary. So it could be 50,000, it could be 100,000, depending on how large dictionary you use. So this is a normalizing term, and given given all the words expected, compatibility, like this is exponential form. So given all the words compatibility with this particular target word, you want these neighboring words to have a more higher, like a stronger compatibility or stronger occurrence probability as opposed to the normalizing term. So that's the spirit here. So this is just 2 lines of code, 1 and 2, and that's it. You just go through the entire words, and each word go through the neighboring words. So it's a double loop, and inside this is just a simple log-based log logistics softmax function, and that's it. So it's just 2 lines of code, but it works so well that it somehow magically captures the semantic relationship between the words. Right. This part is actually a bit technical. It used to be that the original word-to-vec algorithm treats the target vector and the context vector or neighbor vector separately. So there's a lookup table for the target words, and there's a lookup table for the context words. So when good becomes the target, when T increases the good, there will be a time where good becomes target. Then A becomes a context or a neighbor, right? In that case, the A will be using a context vector, not a target vector. So there are 2 sets of vectors, or 2 sets of actually lookup tables. So this is what it's saying. There's an input vector, output vector, or more like a target vector and a neighbor vector. So if you use 2 different sets of vectors, I mean, the original author did this because they thought that a word can mean 2 different things when it's in the target or when it's in the context. So it actually, if you train it like that, then it actually does manifest the kind of behaviors. Because when Apple is a target as opposed to a vector, as opposed to context, you can see that it has learned a different values for the vectors. Like this is just a 5-dimensional vector illustration, but not but not a lot of people actually do. I don't think anyone does this anymore. Like using different lookup tables for the context vectors and the target vectors. Even in my experience, it doesn't make a bit of a big difference. So, but this is just a technical detail, right? And softmax implementation is this also like these are a bunch of like old tricks that used to be a big thing back in the day when word2vec was such a big thing. So you can see that there's a loop over the entire word, the entire vocabulary, and this becomes a computational bottleneck. So there were some tricks to actually handle that, and one is to use something called hierarchical softmax, which is kind of using like like binary trees, and there are this is a bit way more popular technique, which is negative sampling. So as I said, this is a normalizing term. So instead of going through all the words in your vocab, you just randomly sample 10 words or 5 words to just estimate the whole vocab, which actually works pretty well, actually. So you just need to predefine the hyperparameter K, like how many negative samples you're going to draw from the entire vocab. Right? And so what good does it bring you? So once you've trained word-to-vec vectors, like skipgram vectors, aside from doing this king minus men plus women giving you queen, aside from those fun little experiments, what good is it? So people tried to use it for various downstream tasks because all NLP tasks are based on words. So as I said, word is the basic unit for processing text. Not these days. We use subwords, but before like 2017, 2016, when subword became a thing, everything was based on words. So word is the basic unit of processing. So if you have a good representation of words, then you can probably stick it in, like plug it into all the downstream tasks that use words. So such as translation, part of speech tagging, sentiment analysis, clustering, like like all like do we have translation? Yeah, machine translation, chatting, all kinds of stuff. So illustration wise, for example, we haven't learned RNN yet, but I'm just gonna draw it anyway. So for example, this will be, let's assume you're doing a document classification with RNN architecture, and you have no, not Samsung released new Galaxy. So Samsung released new Galaxy. So Samsung, there's a corresponding word vectors for each word. So Samsung has its corresponding vector. Release also has a vector. New also vector. Galaxy. So these are the vectors, and you plug these vectors into the RNN architecture, which would look like this. And this will be H1, H2, H3, H4. And based on that, you can do like clustering, document classification or translation or whatever. So there is a part where you plug word vectors inside your RNN architecture. But this could be RNN, this could be transform, it could be CN. It doesn't really matter. Just some architecture that handles sequence of words. So this part here where you look up the word, the natural language word into a vector, to turn it into a vector, this lookup part is where the word vectors are used. So once you have, and these days people just randomly initialize this, right? But if you, back in the day, like 2013, 2014, when you use word2vec, you can train a word2vec or skipgram vectors and use those skipgram vectors instead of randomly initializing these lookup tables. Then it would give you some performance improvements for certain tasks. Not all tasks, but certain tasks like sentiment analysis, especially these, or like document classification, like some of those tasks that rely on the semantics of each word, they get a really nice improvement by using word2vec vectors, or if you initialize your lookup vectors using lookup table using word2vec, as opposed to randomly initializing it. But it doesn't help all the time. Not all tasks benefit from word2vec, but some tasks do. So people try to see how much you can gain by using word2vec. All right, so we've just talked about word2vec so far, but there's also another very well known word vector or word embedding learning algorithm, which is called GLOVE. So this is called global vectors for word representation. So as it says, it's a global vector, meaning as opposed to how skipgram or SIVO or just word2vec just focuses on its immediate neighbors, like 3 here, 3 here, as opposed to this. GLOVE uses a word co-occurrence matrix. So it goes through the entire document and counts how many times a pair of words occur with each other. Like it's just basically a counting, and then use that co-occurrence matrix here. So P is a co-occurrence matrix, and I and J is the index, because co-occurrence matrix is a two-dimensional matrix, right? So I and J meaning different word index. So this algorithm somehow uses co-occurrence matrix to look at the global information of all the documents and then learn a word representation. So this is way faster because it doesn't have to go through all the document, all the sentence, and go through the context and then calculate the word2vec, the skipgram algorithm. It doesn't do that. It just looks at one matrix and that's it. But in my experience, skipgram gives you a much better result, especially with the king minus queen plus men thing. That's skipgram's like strength. And when like word2vec and all these like glove and this kind of like word embedding thing became a thing, people try to expand that to document level or paragraph level. So there was a paper called like paragraph2vec or doc2vec, and the idea is super simple. So this is the SIBO version of doc2vec. This is the skipgram version of doc2vec. And if you just look at the skipgram version, you just have a document vector, predefined document vector. For example, if you have like 1,000 documents in your corpus, then you need to have 1,000 vectors prepared for each document. So there's certain document number one, document number two. Then document number one has its own vector. And given this document one's vector, you would like to be able to predict all the words inside this document as opposed to words that are not inside this document. So this is exactly the same as the skipgram spirit. And using this algorithm actually works pretty well. So you can acquire like document vectors for like 1,000 different documents in your corpus, and then you can start comparing between similar documents, or you can like estimate how similar documents are based on their like Euclidean distance or cosine similarity. All right, so this is it for word embedding, and we're going to move on to subword embedding or subword encoding. Any questions so far? All right, I guess not. Subword encoding, as I said, this is also a very like a default technique that everybody use by default. Like I don't think anybody not uses, like anybody intentionally not using subword encoding. I can't imagine. So, but it's just how like widespread, how like a fundamental technique this is. So the reason that subword encoding or subword embedding came along is because there are certain, especially for companies like Google, which runs business on multiple countries in handling multiple languages, um, having a unified word embedding system or word tokenization system would be tremendously helpful, right? Because you don't have to develop separate products or separate ML models for different languages or different different cultures. So this is kind of like where that could be like a good inspiration or motivation. So yeah, these are like how different like words are. Like some words don't even have I mean, as I said word is the basic unit of processing text, but that is not the case for certain languages such as Chinese, because Chinese language doesn't have a segmentation, so you can't really tell where the words start and words end, as opposed to like English system languages. And yeah, like yeah, I don't know how you would tokenize this, because there's like I heard that there are certain meanings to all these small dots here, They all have a meaning, so it will be really hard to like segment them into words. So word to vec, or the spirit of using words as a basic unit of processing, always breaks down when it goes to like non-English language. And even within English language, there's always new words popping up, like I'm or good vibes, like especially in the day of like social network, people just twist the words for fun to express their emotion, or just linguistic flexibility, like something for you, like summon for you. If you try to have word vectors for all these new types of like abbreviated words or word plays, your vocab space will explode very, very quickly. So one actually alternative to using words as basic unit of processing is actually using characters, like letters, like A, B, C, D, E, like just use letters instead of words as a processing unit. And actually it works pretty well. So people try to use it back in 2015, 2016, like because they were so tired of handling this kind of like exceptional cases in just human language or natural language. They just thought, if we use characters, like just ASCII codes, like maybe just if you're using letters, then maybe 56, like some number of very small vocab would suffice. You just have uppercase letters and lowercase letters and some Roman, alphanumeric, numeric, like zero like digits, and that would be it. Like maybe less than, like at most like 100 would suffice, as opposed to having to have like 30,000, 50,000, 100,000 words. So that was a bit of a thing back in 2015, 16, and actually gave promising results. So for example, if you use, I think this is a English Czech translation, machine translation, UMWMT is like a competition or like a hackathon. And back then in 2015, word-based model was giving a 15.7 blue score, and character-based model similar or even slightly better performance. So which means that character level model approach does have a certain potential or certain, like it's at least comparable to the word level models. But the problem is it's super slow because if you break this entire thing into character level, this would be how many, like hundreds of sequences, as opposed to if you just break it down into words, this would be when, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, yada, yada, yada. Like probably less than 30 or 40. But if you break it down into letter level, then it's W, H, E, N, I, D, C, I, R, E, like easily 300, 400. So that's the problem of character-based approach. It is very generalizable to different languages, and also it's very robust to these new words or like exceptions or word plays. The problem is it's just too slow. It's too slow. Yeah, 3 weeks to train. This was back in 2015, but we have A100s, but still, it's way slower than, because basically your sequence becomes too long. Comment from Christoph. As a Czech, huh? As a Czech, I can tell that our language is complex. Good. Yeah, yeah, yeah. So this all like linguistic characteristics, these like people say that necessity is the mother of invention. So Google or just linguistics or linguists or computer scientists, they just didn't want to deal with different linguistic characteristics all the time. They just wanted to have a very one strong, robust algorithm to deal with all of them. And word sentence, I mean, subword embedding is one of the inventions. Right, so yeah, we can skip the details. These are all like literal character level architectures. So now we come to subword models. And subword models, I think the very first one was called word pieces, which was developed by Senrich from 2016, 2015. And something else called, so word piece is one thing, and something else called byte pair encoding. So I think these days everyone just uses byte pair encoding. But these two are essentially the same thing. Word piece and byte pair encoding, essentially the same thing. It's just that they have a slightly different objective function. And I think all the GPT tokenizers are based on byte pair encoding. I think BERT tokenizers are based on word piece embedding, word piece algorithm. So what is a byte pair encoding? Byte pair encoding actually is an algorithm for compression. So there is if we think about a communication between two parties, we would like to compress our message to send so that we can, make efficient use of the communication channel and whatnot. So you can think of byte pair encoding as one of the compression algorithms. So there are some high-level algorithm, but I think it's easier to just look at the example. So we go to the example directly. Suppose that you have a set of documents, a corpus, and you just went through all the documents and counted all the words that occurred in the document. And it happens to be that there are only 4 words in your corpus, and these are the number of occurrences. So low occurs 5 times, lower occurs 2 times, newest occurs 6 times, and widest occur 3 times. Right. And actually, I think, yeah, there is a typo here because there are 2 W's here and here. But as I was saying, you go through all the documents and then you count all the words in your documents, and then you have a counting, and then you start with a letter level, like a character level vocabulary. So you take all the unique letters like L, O, L, O, W, E, R, N, STYIWID. I think that those are it, right? So yeah, there should be only one W. So this is a typo. Actually, if we're gonna erase one, it should be the other way. Yeah, yeah. This is a typo. Right. So this is how we start. We have a word counting and we have basic character level vocabulary. And what we do is we start looking at pairs, all the possible pairs of letters. So we look at LO, OW, OE, LN, whatever, like all possible pairs of letters, or not just letters, just vocab, because these are just the vocab, right? And you take the one that occurs most, the most frequent pair and you register it as a new vocab. It's a new entry into your vocabulary. So ES, which is ES, happens to be the most frequently occurring pair 9 times, like 6 plus 3, 9 times. So ES becomes a new entry into your dictionary. So your dictionary is actually increasing by adding new thing into your vocabulary, and the new thing has to be the most frequently occurring things. So the next time you look at all the possible pairs again, like LES, OES, WES, and all the way to like ES and T. ES and T happens to be the most frequently occurring pair for which is 9 times, right? So EST occurs 9 times. So EST now is the new entry into your vocab. So you've gone with ES and EST, and now the next time you look at again, you go through all the pairs, and then the next pair the next most frequently occurring pair happens to be LO. LO occurs 7 times in your corpus. So you do this. So you keep doing this over and over and over again, and until when? Until you are satisfied with the size of your vocab. So usually you have to set a predefined size for your dictionary. Like, oh, I'm gonna have a 30,000 entry dictionary, or 50,000 entry dictionary, or 100,000 entry dictionary. It's up to you. So depending on how large your data is and how like diverse, how multilingual your data set is, you have to like appropriately set the size of your dictionary. Right, so this is the very simple byte pair encoding algorithm. And word piece, what do we have it here? Actually, yeah, before moving on to word piece, like this is the summarization of byte pair encoding. So you have a target size and you stop. So once you hit the target, once you hit, like, you keep increasing it, and once you hit the target, so for example, like 50,000 entry dictionary, then once you hit 50,000, you just stop the for loop, and that's it. And it's yeah. The good thing is that it automatically decides the vocab for a system. So you don't have to have any linguistic knowledge of a given language. For example, if you're given a bunch of Korean documents and you want to have a Korean dictionary or Korean vocabulary, you don't need to know any single Korean word at all. You just run this very simple compression algorithm until you're satisfied with the size of your vocab, and that's it. And it'll be linguistically sensible, because it's based, even though it's like very simple based on like counting is still a very powerful concept. So these, if you look at like the ones that are added here, like EST is actually a frequently occurring like a stem. It's like a subword, like strongest or widest, newest, because so EST is certainly has a meaning, right? So even though you don't know anything about English or Korean or whichever language you use, it'll still give you a linguistically informed vocabulary. Yeah, so that's what it says. Automatically decide. So this is all good this is like, beneficial algorithm for engineers who has no linguistic knowledge at all. You just want to have a vocabulary system, and then you tokenize your documents, and then put that into your LLM, and then train it, and you're good to go. You don't need to know anything about language at all. We're living in this era of scale, not domain knowledge. And this is like one like very important piece that enabled that kind of like attitude or spirit. Word piece or sentence piece. So this is as it says here, rather than simply counting the word, the pair of vocab and adding it into your dictionary, it actually has a different like objective, which is to you choose the pair. So when I say pair, I'm just saying all these like pair of words, right? Pair of letters. When you're choosing the next pair to add into your dictionary, don't just use the most frequent one, but use the one that maximizes actually reduces perplexity, like maximizes language model log likelihood, which is the same as reducing perplexity. So basically, just you want to have a better explainability of your document by adding the one that gives you the minimum that maximally reduces perplexity. So that's a little bit more like information theory inspired, but I'm pretty sure like these two, like the word piece versus byte pair, not much of a difference. Which because we know that GPT used byte pair encoding instead of word piece, so it doesn't really matter. All right, so word piece and sentence. There's something called word piece, and there's something called sentence piece. Sentence piece actually treats, this is also technical detail. Sentence piece treats a blank or a space, white space, also as a token. So white space is retained as a special token. So it's a little bit more like even more robust than the word piece or byte pair encoding. So because it doesn't even care about the segmentation, it like because a space is a letter, so it's a little bit more robust algorithm. Right, and yeah, here is BERT uses variant of word piece. So if you so you can imagine what would happen if you have like millions of documents and then you run a word piece for like byte pair encoding and then you've obtained a 50,000 size dictionary, then it would like, most of the time it'll be filled with very frequent words. Like frequent words will not be broken down into subwords. For example, like boy or girl or tiger, car, truck. They won't be broken down into like I'll just write it here. Like boy will be a boy. It won't be broken down to B or OY because boy is such a frequently occurring word in English documents or English corpus. It will not be broken. It'll just be it will be registered in the dictionary, as opposed to like very complex words like, well, like this. Like I don't know what hypatia or hypatia is, but I guess this is an actual example. Like Hypatia would be broken down into these four subwords because Hypatia is such a infrequently occurring word it's a rare word. So rare words don't have a chance to be registered in the dictionary. So it'll have to be broken down into different parts like H, YP, ATI, and A. And the sharps here and these pound signs here are just to say that this is not at the beginning of a word. So H doesn't have a pound sign because it's beginning at the beginning of the word, and the other are in the middle of the or intermediate or the end of the word. So it's just pound signs are just to indicate that. Anyway, you can see the intuitive results of using byte pair encoding or word piece. Like frequent ones will be registered as or just itself, but the infrequent ones will have to be broken down into multiple parts. But the good thing is there will never be a out of vocabulary situation. Do we have it? Do we say it here? Okay, unfortunately, I should have mentioned that. Sorry about that. Yeah. So yeah, I should have mentioned that when we were talking about character level. So if you just use word level, well, word level approach, like these like, new words will give you an out of vocabulary problem, OOV problem. But if you use character level or word piece or byte pair encoding, as for that matter, you will never run into OOV because any word can be broken down into subwords, right? So there won't be a OOV situation. So that's the beauty. Yeah, that's the beauty of all these subword encoding models, subword encoding algorithms. Okay, so I think we cannot end a bit earlier than usual because the last one is contextualized word embedding, and I just have 2 slides here because this is the introduction to what we're going to learn in BERT class. So before we do this, any question about subword encoding? No, then yeah, we can move on to contextualized word embedding. So this is exactly what who asked me that question about homonyms? Yeah, Kang Jae-hoon. This is what exactly this is exactly that situation what Kang Jae-hoon talked about as regarding the homonyms or the words that have the same surface form but have 2 different meanings. So this is you can think of this as a model, like AI model, and this is a user, and let's say this is a word to vec. This is word oops word to vec, and this is a user. And the user wants to look up a specific word vector, right? In that case, what's the embedding of the word stick? So what's the embedding of the word stick? If it was word2vec, then word2vec will have already predefined once the training is done for word2vec, you just have a static vector for all the words. There's a corresponding vector for each word. So if it was word2vec and the user asks for a stick, it'll just give you a stick vector and that's it, right? But this is actually something called Elmo. Elmo is the very first contextualized word embedding algorithm, kind of like a predecessor to BERT. So this is Elmo. And Elmo, what's the embedding of the word stick? Then the Elmo obviously says there are multiple possible embeddings. Use it in a sentence, which is a great question because, for example, stick. I said that stick can mean two things, like a wooden stick and also sticking to a wall, right? So we need to actually give a example or the context of how we want to use it in the end, not just the word itself. For example, to handle homonyms to begin with. So use it in a sentence, and the user says, "Oh, okay, I want to use it in this sentence. Like, let's stick to improvisation in this skit." So in this case, this stick means like attaching to, or like start attaching to a wall. That kind of meaning. So what Elmo does is then, okay, in this case, in this sentence, specific sentence, then sticks embedding should have this value. So that's what Elmo does. So what Elmo is actually, this is Elmo, and then this is BERT, and this is GPT-1. So these are all three different variants of contextualized word embedding. So contextualized word embedding, meaning you have to give the context so that you have to use a context to actually retrieve a much better, much accurate, like semantically accurate word embeddings. And Elmo uses two RNNs, forward RNNs and backward RNNs. BERT uses, actually OpenAI's GPT-1 uses transformer, but it only goes this way, like autoregressively, obviously. BERT uses transformer, but it's bidirectional. So that's why it's B, like bidirectional embedding something I forgot, you know. Anyway, so that's the spirit of Elmo, GPT-1, and BERT. And then BERT and Elmo, they serve exactly the same purpose. GPT-1 tried to replace Elmo, but failed, and then it just went its own way and then became 2, 3, 4, and now we're here. A question from Hyung. Isn't GPT based on transformer decoder? Yeah, so you can see that it's only going this way, right? Like it only goes the attention only goes into the future. Well, I mean, it should be the other way. I mean, so this guy can only look into the past, and this guy only can look into the past, and this guy as well, and this guy as well, right? So you can think of this as a transformer decoder. So BERT, we haven't even looked at transformer, but as a like a sneak peek, like a very short preview. Transformer consists of encoder and decoder in order to do translation. So encoder takes in English and decoder spits out like Korean. So that would be translation. And BERT happens to use only the encoder side, and GPT happens to use only the decoder side, but not exactly the same decoder as transformer was proposed. But we'll get to that. So just suffice to say that Elmo is the very first model that tried to have a word embedding generator, so to speak, word embedding generator that takes in a context and gives you back the exact, more accurate word embedding, word vector, as opposed to word2vec, which is a static word embedding generator. It's just a lookup table. But this Elmo is not a lookup table, it's a word embedding generator. So it used RNN, and then GPT saw Elmo and thought it could replace the RNN with transformer, and then came up with GPT-1. And then Google saw GPT-1 and thought maybe they could just bidirectionalize it, and then that's it. So this is how history happened in 2018. And you know the rest. BERT was relevant for like a couple years, and then GPT 3.5 came along as a ChatGPT, and then now we're here. All right, any question? This is the end of the class today. So if you have somewhere else to go, you can leave. If you have any question, please let me know. We can wait for I'm gonna wait for maybe 20 seconds in case someone's typing stuff. So as a summary, today we all just taken a like a stroll down the history, like we just did like a history lesson on the word embedding and the subword embedding and how we came to how we will eventually come to BERT. And this practice session, you'll probably like train word to vec and then do the linear operation, like the king minus man plus queen. I mean, woman plus queen. You'll actually get to do that on your own. All right, I guess there are no more questions then. All right, thank you guys. I'll see you next week then. Bye-bye. 네, 감사합니다. 네. 네. Thank you. Bye-bye. 네.